Hello students and welcome to the lecture. So students, if you look at it here, you will find out that basically in this lecture, we are going to start the topic of work, power and energy. This is going to be a part one. Okay. In this lecture, we will discuss about the work, the power and the energy in the part one. Okay. If we talk about the point of discussions that we are going to have here, so we will talk about the introduction to these areas. Then measurement of work that we will discuss about. Okay. Units of work we will discuss about. Power we will discuss about. Units of power we will discuss. And energy we will discuss. And at last we will discuss the summary of all of these. Okay. So this is going to be our point of discussion. But before starting this, there is a small disclaimer that is presented over here that we are required to discuss first. That disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Okay? Now, let's begin with the introduction. So basically, whenever we talk about the work, so the meaning of the word work is actually a quite different in the common language that we use. But whenever we talk about the physics or whenever we look at the word physics from the, at the word work from the physics point of view, then basically the meaning is quite different that we use in the common language. Okay. Like in common language, if you are doing any physical activity, if you are doing any mental activity, we usually call it as a work, that this person is doing some work. Some work is going on there. Okay. That is what we use in a common language. In physics, the work is not defined by this criteria. The work having a different meaning here. The work is defined here by the scientific meanings and scientific terms that are associated with the physics. Okay. For example, if we talk about the normal common language. So if a coolie taking a load on his head from one end of the railway platform to the other. Okay, like here you can say, this is the coolie. You can say he's carrying the bags and the attaches over his head on his shoulders, and he is moving with this bag from one point to another point in the railway station. Mostly time, if you visited the railway station, you see this kind of thing. So generally, if I ask you like what this person is doing, what will be your answer? You will simply say that this person is doing some kind of work, right? But when we take this into the consideration as per the scientific terms and the criteria that we have in physics, so we could say that he does not do the work. So here you can say that you are getting little bit contradiction. In a common language, you are saying that this person is doing a work. Okay. Were you seeing the coolie is carrying the bags and all, or the weight on his head, on his shoulders, and he is moving, he's doing some work. But in physics, we are saying that he's not doing any work. So contradiction is there because our common principles, our common belief that we have associated with the term work in the common way, this is actually being challenged when we take it to the physics way, right? Why it is happening? Because in physics, work is said to be done if a force acting on a body is able to move it through some distance. Okay, like you can say, physics will not admit that the coolie is doing work. Why? Because these attaches and all that you are seeing, this is the weight he is actually carrying, or this is the body he is actually carrying. Is there any external force being applied on them? Even if we talk about the coolie, is there any external force that is being applied on his body? so that he could move. No, he is moved by himself. There is no force that is being applied here, which is making the body to move through some distance by itself. That is why in physics, we could not call it as a ongoing work. In a common language, yes, we do call it as a ongoing work. Therefore, work is said to be done only when the force applied to a body makes the body to move. If this condition is not there, as per the physics, we could not call it as a work. When we could call it as a work? When the force that is being applied to the body, making the body to move. If it is not there, body is not moving. And body is not moving, no work is going on. That's it. Now, after taking the introduction of work, like what is the work in actual? The another thing that we are required to understand over here is how do we measure the work? And that is we will understand under the measurement of work. The amount of work done is equal to the product of the force and the displacement of the point of application of the force in the direction of the force. Like you can say force into displacement. In the normal point, we could say, suppose if you are seeing any object in front of you, okay, just take the example. There is a book that is being kept on the table. Okay. So if you pushes the book and the book moves, it means previously the book not having any kind of additional force. When you pushed it, you applied that additional force. That additional force makes the book to move. It means the point where the book was initially, the book displays from this point to some point. Okay. And this point will be in the direction of the force that you have applied. If you push a book in the right side, the book will go to the right side. If you push the book left side, the book will be go to the left side. So now you can say not only the force you have applied, but also you have applied a force with some direction. While you are pushing right direction. While you're pushing left direction. So work is actually the product of the force that is being applied and the displacement that the body has taken from this force in that direction of the force. Okay, that's why it is known as the F into T. For example, only we could say you applied 2 newtons force, okay, and the book moves 5 centimeter, okay, as a displacement. So how much work you have done? 2 into 5, 10 Newton centimeter. That will be our work, hypothetically speaking, or you can say just as an example, if we consider the SI units of force and the displacement. Got it? Here work done is W, being denoted by W. Force F and D is equal to displacement. Okay? Where F and D are magnitude of the force vector and the displacement vector respectively. F is the magnitude of the force that you have being applied, like we had taken the example. 2 Newton is the magnitude of the force that you have applied. Displacement vector, if the book moves 5 centimeter, that is the displacement vector. Okay, the displacement being in the direction of the force. Like as we had discussed, while you're pushing the book, you pushed it in the right direction. Right direction displacement will be there. You push the book in the left direction displacement will be there. Got it? Now, in case force F acts along a direction making angle 0 or theta with the, actually it's a theta, not 0, with the direction of displacement D as shown in the figure. Here you can see. Okay. Then work done is found by resolving the force F into 2 rectangular components. Okay. Fx along the direction of displacement D. Here you can see Fx such that F is equal to F cos theta. Fy along the perpendicular to the displacement. Here you can say if this is the displacement rate, this is the perpendicular to displacement. Such that Fy is equal to F sine theta. Okay. As the body does not move in the direction of component Fy, the component Fy does no work. On the other hand, work done by component Fx is given by W is equal to Fd cos theta. Like you can say, what is the condition of being said that the work is being done? What is the condition? External force must be applied. Displacement must be there. Displacement must be in accordance with the direction of the force being applied. Book was there. You pushed it, applying the force. You pushed it, the book moved, displacement happened. If you push the book in the right direction, the force is being applied in the right direction, book will displace in the right. If the force being applied in the left direction, displacement is in the left direction, the book being displaced in the left. Okay, so direction of the force must be aligned with the displacement. If this condition is not being satisfied, no work will be done. Like here you can say, we have taken Fx and Fy. Fx means cos theta, Fy means sin theta. So here you can say, if you look at this displacement angle, this is in this right direction. If we consider Fx as a force, the movement is in the right direction. The force is being applied in the right, the object displays in the right. Here the work is being done because the object is moving in line with the direction of the force being applied. Whereas Fy is not a work associated. Why? Because the object is moving in this direction, the displacement in this direction, not in this direction. Got it? In figure, F vector and D vector are in same direction. Therefore, theta is equal to 0 degree. Then work is equal to F into D cos theta is equal to Fd, or W is equal to force vector into displacement vector. Got it? As work done is not product of the vectors, it is a scalar quantity. Also, when force vector and displacement vector are perpendicular to each other, okay, like in this condition, this is the force vector, this is the displacement vector. If you look at here, you will find this is the perpendicular. Okay, they are perpendicular to each other. Got it? Then in such a scenario, force vector into displacement vector cos 90 degree because of the perpendicular is equal to F into 2 into 0 is equal to 0. Which means if a body moves in a direction which is perpendicular to that in which the force acts, the force is being applied in the right, the body is moving in the north direction, then the alignment of force being applied and the displacement caused is not in the same direction. The force does no work. That will be our observation. So I hope now you have got why this Fy and Fx is important to understand in which condition the work done or in which condition the work is not done. If they both are in the same direction, the force being applied and the displacement, the work will be done. If they both are perpendicular to each other, the force being applied and the displacement is perpendicular to each other, no work will be considered. Got it? Now, what is the units of work? This is the another thing that we have to deal with. What is the units of work? So the SI unit of work is the joule. Okay, joule is the SI unit of work. 1 joule of work is said to be done when a force of 1 Newton displaces a body through 1 meter in its own direction. Okay, like if you look at this, 1 Newton is the SI unit of force into 1 meter is the SI unit of displacement. 1 into 1, the work will be 1 and 1 joule. Okay. MKS unit means meter, kilogram and second units. In MKS system, the unit of work is equal to kg m square S minus 2 or S power minus 2 basically. CGS, centimeter, gram and seconds units. In CGS system, the unit of work is erg. 1 erg of work is said to be done when a force of 1 dyne displaces a body through 1 centimeter in its own direction. Now, it is my request to all of you, kindly do not get confused between this observation that you have on this slide with the example that we have taken in the initial, where we said the 1 Newton into 1 meter. You will said that we had taken the 1 meter there as a displacement unit, 1 Newton as a force unit, and we said this is the international unit or SI unit. Please do not get confused in them. That was just an hypothetical example. Even I have told you the same. Basically, if we go by the SI unit, the work SI unit is joule, force is 1 Newton, displacement is 1 meter. MKS unit, work unit is equal to kgm square S power minus 2. CGS unit, work unit is erg, force unit is 1 dyne, and displacement unit is centimeter or 1 centimeter. Okay, kindly keep your concept in a crystal clear way. Relationship between the joule and the erg. 1 joule is equal to 10 power 7 erg. Nature of work done in various situations. Work done is given by work is equal to force vector ratios displacement vector. Okay. Therefore, work done could be positive, negative, or zero, depending on the angle between the force vector and the displacement vector, acute angle, obtuse angle, or 90-degree angle. So, based on these three angles that will be formed between the force vector and displacement vector, the positivity, the negativity, and the neutrality or zero of work will be defined, whether the work is positive, negative, or zero. Also, the work done is zero when either force vector or displacement vector or both force vector and displacement vector are zero. Okay, like if the force is zero, displacement vector will be there, but also zero. Force is zero, displacement vector is zero, zero. Okay, the work done in stretching a spring through a distance x is given by W is equal to 1 by 2 k square, where k is spring's constant. And remember that will always a small k, not a capital K. Okay. Now, after discussing over the work, it's a time to start our discussion with the power. So if we talk about the power, many times we have a conception like power is the muscle power, physical power, mental power and all. No, common language, normal language. But in the scientific terms, when we take this into the consideration of physics, what do we understand by the term power? That is what we are required to understand. Power is basically the rate of doing work is called the power. Therefore, power is equal to work by time is equal to force into displacement by T is equal to F into V. Thus, power depends on the time for which the work is done, while the amount of work done does not depend on the time. If you go by the works formula, have you seen the timing there? No, there was only a force vector and a displacement vector. But in power, basically, we are talking about the rate of doing work. We are not only talking about the work is happening or not happening. We are talking about, okay, the work is happening, but at which rate? At which speed it is happening? So that's why the time is being considered in the power, which may not considered in the work done. For example, if a coolie A takes 1 minute to lift a load to the roof of a bus, while another coolie B takes 2 minutes to lift the same load to the roof of the bus, then you can say the work done by both the coolie is the same. Coolie A did the same thing while coolie B did the same thing. But the power used by coolie A is twice the power used by the coolie B. Why? Because A takes only 1 minute to do the work, while B takes 2 minutes to do the same work, which means A's efficiency is more than the B's efficiency, or in You can say in context to this, we could say A's power is more than the B's power. Power is also the scalar quantity. Why? It only measures the magnitude, not the direction. Now, what are the units of power that we are required to understand? So, the SI unit of power is what? It is named after a famous scientist, James Watt. Okay, what is the unit of power? 1 joule of work is done, then in 1 second, the power is said to be 1 watt. Okay, in the MKS unit, the unit of power is kgm square s powers minus 3. In CGS unit, the unit is power is erg per second or erg s powers minus 1. Relationship between the SI unit and the CGS unit, 1 work equal to 1 joule second minus 1 equal to 10's power 7 ergs minus 1 is the power. Okay. Note, another unit of power largely used in mechanical engineering is horsepower. Okay. Like you can say, if you are the fan of the supercars or automobiles, then you must have heard about this term. Like everyone knows the name of Ferrari. Okay. When we talk about Ferrari, we say that Ferrari is so powerful. Ferrari is having a powerful engine. How do we define the power of Ferrari? With the normal cars that we have. Suppose if you can say, if there is a normal car standing by you and there is a car Ferrari standing by you. And if I ask you, what do you think which car is having the more power? What will be your answer? Your answer would be that this Ferrari is having the more power than this normal car. How? Because you will talk about the HP or the horsepower. Like Ferrari is having the 1000 horsepower. Okay, that's why. And the normal car is having only 100 or 200 horsepower. That's why. So accordingly, the Ferrari, because having the more horsepower, it is more powerful than the normal car. Okay, and this horsepower is basically given by the James Watt. And 1 horsepower is equal to 146 watt. Is equal to 146 watt. All right. Kilowatt hour is the unit of work and not of power. Remember, kilowatt hour, because watt is including here, do not get confused that it's a unit of power. It is actually the unit of work, not of power. 1 kilowatt hour equals to 1000 watt hour, where 1000 into 3600 watt per second is the equation. Or you can say 3.6 into 10's power 6 watt seconds equals to 3.6 into 10 की power 6 joules. Okay. Note, watt, kilowatt, megawatt and HP horsepower. These are the unit of power, while watt second, watt hour, kilowatt hour, these are the unit of work, not the power. Again, let's look at them. Watt, kilowatt, megawatt, horsepower. Unit of power, while watt second, watt hour, kilowatt hour, unit of work, not the power. Got it? Clear? Now let's move ahead. Now, energy. Energy is also, whenever we talk about the energy, what do we think? That energy is the physical strength, right? Or the mental strength. Like if I ask you, do you have fever? You said, yes, sir, I have a fever. So what I will say, today you will have a less energy. Because mentally or physically, you are not that much of capable to performing the task that you will be on when you have good health, right? So in local language or in common language, basically we associate the energy with the, you can say, physical and mental strength of a person. In scientific terms, whenever we talk about the energy, so we define it as the capacity for doing the work, like up to which capacity the person could doing a work. That is actually the energy. Okay. Energy is also a scalar quantity because it only measuring the capacity or magnitude, not a direction. Okay. Its dimensional formula is m into L square into T minus 2. Therefore, same as that of work, and it is measured in the same unit as work. Therefore, joule in SI and erg in the CGS system. Further, energy and power are different from each other. Whereas, energy of the body is the total amount of work that our body could do and does not depend on the time in which the work is performed. The power of the body depends on the time in which the work is done. Okay. Energy could exist in various forms, such as the mechanical energy, heat energy, light energy, sound energy, electrical energy, magnetic energy, nuclear energy, etc. Okay. This is the existed forms of the energy. They are described below. If we go by one, first type is the mechanical energy. Mechanical energy is the energy possessed by a body due to its state of rest or the state of motion is actually called the mechanical energy. Okay. Or we could say the energy that is being presented in the body because of the state of rest or of motion. Mechanical energy is found in two forms, the potential energy and the kinetic energy. The total mechanical energy of the body is the sum of the potential energy and the kinetic energy. You can say these two types of energy, potential energy and the kinetic energy, presented inside the body, and the sum of these will be the total mechanical energy. First is the potential energy. So the energy possessed by a body by virtue of its state or position is called the potential energy. Okay. For example, a wound up watch spring has the potential energy because of wound up state of its coil. Okay. So that is basically because of the state and the position, the energy is there. Whereas this form of potential energy is the elastic potential energy, and it is equal to the amount of work done in winding or compressing the spring against its elasticity. Similarly, a bent bow, a stretched rubber, etc., these also having the elastic potential energy. A compressed gas has the potential energy due to the attraction between its molecules. A stone placed at a height has the potential energy stored in it because of its position at height. When a stone is lifted from the ground to a certain height, work is done against the force of gravity. Okay. The amount of work done is stored in the stone in the form of its gravitational potential energy. Potential energy of a body at height h is given by equal to m into g into h, where m is the mass of the body and g is acceleration due to the gravity. When an air bubble rises in water, potential energy of air bubble decreases. Why? Because work is done by upthrust on the bubble, and that is being converted into this. The PE or potential energy of an object could be negative when forces involved are attractive. Now we have the kinetic energy. So the energy possessed by a body by virtue of its state of motion is actually the kinetic energy, measured by the amount of work done by an opposing force in bringing the body to rest from its state of motion. If m be the mass of body having a velocity v, the kinetic energy of the body could be given by kinetic energy is equal to half mv square is equal to 1 by 2m into mv square is equal to p square by 2m. Okay, where r is linear momentum. Here kinetic energy is inversely proportional to m into, and kinetic energy is inversely proportional to v square or p square. Thus, if the mass of the body becomes double, then kinetic energy will become double. If while velocity or linear momentum becomes double, the kinetic energy becomes 4 times as that of the original. Okay, and please correct it. It is not inversely, it is directly proportional. Okay. Now the potential energy changes into the kinetic energy when it is put to the use. Conservation of mechanical energy, we talk about it. So we could say the total mechanical energy of a body at any instance is equal to the sum of its kinetic energy and the potential energy. Because we have just, you can say, learned it while we starting the discussion over the energy. According to the law of conservation of mechanical energy, whenever there is an interchange between the potential energy and the kinetic energy, the total mechanical energy, therefore, the sum of kinetic energy and the potential energy, remains constant when there are no frictional forces. Dissipation of energy. In transformation of mechanical energy, if a part of it gets converted into another such form of energy which couldn't be utilized for useful work, which means the part may be, you can say, converted into another, but couldn't be put on the useful use. The loss of energy is called the dissipation of energy conversion of one form of energy into the other form. Following are some examples of conversion of energy from one to other form. First is mechanical energy to electric energy. So if we talk about the receiver of a dam, so because the water is being stored at certain height, so that is having the potential energy. When the water falls, which means the water is losing its height, means the potential energy, and coming down, which means in a motion, then the water energy from potential, it's transferring into the kinetic energy. Okay. If the following water is made to rotate a turbine at the bottom of a dam, the kinetic energy of water is being transformed by the turbine into the electric energy. Okay. An electric generator or dynamo converts the mechanical energy into the electric energy that is used in the various household or commercial uses. Thereafter, the electrical energy to the mechanical energy. So if we talk about the electric motor that is being powered by the electricity, basically the electrical energy is being consumed in the motor and the motor is performing some mechanical things. That's why electric energy is changing into the mechanical energy. The electric motor is used in many rotating devices like the fan, washing, etc. Electrical energy to the heat energy. In electric appliances such as the electric heater, oven, geyser, toaster, etc., the electrical energy changes into the heat energy when in use. Because these are being powered by the electricity, so that means they are consuming the electrical energy. And because they are heating the objects, which means they using the electrical energy and converted it to the heat energy for doing the work. Electrical energy to the sound energy. If we talk about the loudspeaker and electric bell, etc., whenever they use, they converts the electric energy into the sound energy. Thereafter, the electrical energy to the light energy. When an electric bulb glows on passing electric current through it, the electrical energy changes into the heat energy, then into the light. Because if you talk about the 100-watt pulse that we used in the previous time still in the current, so you can say basically whenever these bulbs glows up, they are not only giving you the light, but also they warms up the place because they are being heat up. Okay. Light energy to the electrical energy. In the photoelectric cell, the light energy basically getting converted into the electrical energy. Similarly, in solar cells, the light or solar energy changes into the electrical energy. Heat energy to the mechanical energy. In a steam engine, the chemical energy of the coal first changes to the heat energy of steam, and then the heat energy changes to the mechanical energy. Chemical energy to the heat energy. When fuel, such as wood, coal, gas, etc., they burns, the chemical energy changes into the heat energy. Chemical energy to mechanical energy. In automobiles, while in motion, the chemical energy of the petrol or diesel changes into the mechanical energy. Sound energy to the electrical energy. A microphone basically converts the sound energy into the electric energy and then passes it to the receiver. Chemical energy to the electrical energy. In an electric cell, when current is drawn from it, the chemical energy basically that was previously stored in the cell is totally converted into the electric energy and no more conversion is left. Electrical energy to the chemical energy. While charging a battery, the electrical energy changes into the chemical energy. Light energy into the chemical energy. The light energy from the sun is observed by the green plants, store it in form of the chemical energy. Note, whenever there is a conversion of mechanical energy to the other forms of the mechanical energy is in the form of kinetic energy, because kinetic energy is associated with the movement, and the potential energy by itself couldn't be transferred from being mechanical to any other form. Here we have finished the topic, not part for the summary discussion. We have talked about the concept of work, like how we define the work in physics, like the angle of force and displacement at angle theta, work as a scalar quantity, what is power, what is energy, mechanical energy existence as potential energy and the kinetic energy, law of conservation of mechanical energy, transformation of energy, examples of transformation, and dissipation of energy. With this note, we have completed this part 1. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.